Welcome back. Up to this point, we've been analyzing text mainly by word counts and parts of speech and other techniques. For example, to create a word cloud, stop words are removed, then the text may be further restricted to certain parts of speech, then word frequencies are calculated so that words occurring more often are larger in the word cloud. All of this is a bag of words approach to NLP. Word order is not considered. In the last video, we did consider word co-occurrences in collocations, two words that appear next to each other and seem to convey more than the sum of their individual meanings. The next logical step is learning about text from sequences of words. What word would you use to fill in the blank here? Chances are you thought phones. One of the ways that people learn is by pattern recognition. Hearing "turn off your phone" many times in different contexts, movies, meetings, airplane landings, reinforces this pattern. Context is important. In a movie theater, "turn off your phones" makes sense, but on a website, a more common pattern might be "turn off your ad blocker." If you type "please turn off your" into Google, phone is one of the top suggestions. NLP applications can learn these patterns as well, but how? The answer in many NLP applications is ngrams. Ngrams are sliding windows over text, looking at n words at a time. Unigrams take one word at a time. Bigrams take two words at a time. Trigrams take three words at a time. And above 3, they're usually just called ngrams, with n specified as 4, 5, etc. Ngrams can be used to create a probabilistic model of language. In order to learn a language model, a corpus is needed. The choice of corpus will greatly influence the language model. A model learned from Shakespeare will be quite different than a model learned from a science textbook. Let's look at a toy corpus here, which is part of an old nursery rhyme. Jack be nimble, Jack be quick, Jack jump over the candlestick. We can get unigrams easily enough by just tokenizing. And notice we are including punctuation in our unigrams. We can get bigrams by using a list comprehension. nlp08 has a function that will do this for you. You call ngrams with your list of tokens, and you specify n as the second argument, and then convert all that into a list. And we see we get the same results. The ngram model is a probabilistic model. Probabilities mean we'll need to do some counting to determine how likely words are. So we need to create a dictionary of unigrams and a dictionary of these bigrams. Here I did a dictionary comprehension, where the key is the token and the value is the count. And here I use a dictionary comprehension to create the bigram dictionary. The key is going to be the tuple of the two tokens, and the value again is the count. Notice that period Jack has a count of 2, even though Jack did start 3 sentences. In some language models, they may use start and stop symbols for each sentence to overcome this problem. However, we're just going to use a stop symbol of the period at the end of the sentence. And if you had a really large corpus, it wouldn't make that big a difference. Now that we have counts, we can compute probabilities. What's the probability of Jack B occurring in this corpus? It's the probability of Jack times the probability of B given that Jack was the previous word. More generally, we say that the probability of word 1 followed by word 2 is the probability of word 1 times the probability of word 2 given that word 1 was the previous word. And how we actually compute these probabilities is with the counts. So the probability of word 1 is the count of word 1 divided by the counts of all the words, And the probability of word 2 given word 1 is the count of the number of times word 1 followed by word 2 occurs, followed by the count of how many times word 1 occurs. What if you wanted to know the probability of a certain sequence of 4 words, words 1 through 4 here? That would be the probability of word 1 times the probability of word 2 given word 1 times the probability of word 3 given that it was preceded by words 1 and 2 times the probability of word 4 given that it was preceded by words 1, 2, and 3. That would require counts for all of those things, and the calculations would become very messy. What we can do is take the Markov assumption that the probability of a word is conditioned only on the prior word. So now our probability of this sequence of 4 words is just probability of word 1 times the probability of word 2 given word 1 times the probability of word 3 given word 2 times the probability of word 4 given word 3. And we can generalize this as follows, just multiplying all of the probabilities of the word given the previous word. What would happen if one of the probabilities was 0? Since we're multiplying all these probabilities together, that would zero out the whole probability. This is our probability of a given word. It's just the count of that word divided by the total number of tokens. And if we train on a corpus, and then we try to apply a language model to new data, some of that data may not be there, leading to a 0 probability. We can get around this by smoothing. The idea of smoothing is we're going to take a piece of the probability space and redistribute it so that we don't have 0 probabilities. And there are many ways to do this. One of those is Laplace smoothing, where we always just add 1 to the numerator, and to kind of even this out, we'll add our vocabulary size to the denominator. There are other methods of smoothing as well. So at this point we have trained a model on our tiny corpus, and training in this case only included gathering counts for unigrams and bigrams. But now that we've done that, we're ready to compute probabilities on new data, which we'll call our test data. Here's a function to implement the formulas we just looked at, as well as smoothing. So the function will take in a new text item, and the previous dictionaries we trained on our training data for our Unigram dictionaries and our bigram dictionaries. We'll also need N, the total number of tokens in the training data, and V, the total vocabulary size in the training data. We're going to take our text and create unigrams and bigrams from that. We're going to use Laplace smoothing and a variation of a good Turing smoothing, and we're starting off at 1 because we're going to be multiplying probabilities. An alternative to multiplying probabilities is to add the log of the probabilities. So we'll start off that with 0. This can be very helpful in preventing underflow by multiplying very small probabilities. We're going to loop through the bigrams in our test item. Our numerator n will be the count of that bigram if it's there, otherwise it's going to be 0. If we're using the modified good Turing smoothing, we're going to let our numerator be 1 over n if it's 0. And same thing for our denominator. Our denominator is going to be the count from the Unigram dictionary if it's there, otherwise it's going to be 0. In our Laplace smoothing down here, we'll multiply by our numerator plus 1 divided by our denominator plus v, so we don't have to worry about dividing by 0 for the Laplace smoothing. For the good Turing, we're going to do one of two things depending on if the denominator is 0. If it's not, we're going to do our usual, and if it's 0, we'll take into account. And for the log, all we have to do is add the log. These two should get the same results. All right, then we'll print out our results here. Now let's run it on a sample text. Let's try Jack Be Nimble. The probability with Laplace smoothing wasn't very good. It was 0.009. The Laplace smoothing adjusted the probabilities too aggressively, So that wasn't good. And we see that the probability is much better for the modified good Turing. But still, that's a low probability for text that was actually in our training data. And that's actually an artifact of the reality that our training data was ridiculously small. Now let's try a phrase that's actually not in our training data, Jack be smart. And we see that we got lower probabilities. That's good. So it's less likely to see this than to see Jack be nimble. So even on a toy data set, we see that we can learn something in a language model. We just use ngrams to calculate the likelihood of a phrase. What else can we do with ngrams? Can we use it to generate text? I'm going to show you a very naive approach that doesn't work very well, but it gets you thinking about how to use ngrams. So I'm going to go ahead and create dictionaries of the probabilities of unigrams and bigrams. And here's my naive generation function. Given a start word, it will keep finding the next most likely word until it's nothing left to find. So here, starting with Jack, I get Jack be nimble. If I start with over, I get over the candlestick. Let's look at NLT's generator function. So I'm going to create a text object over our tiny corpus about Jack, and then generate. And we see kind of a lot of nonsense here. So the takeaway is that you need a bigger corpus to get more interesting results. So let's do that. I'm going to use text4, which is inaugural address corpus, and generate from that. And that's what we see here. And this sounds very much like the language, but it doesn't completely make sense. Generally, the bigger the ngram, the better the results. In other words, trigrams will get better results than bigrams, and higher ngrams can work better still. Ngrams are good for predicting the next word in a series of words, and this can be very helpful in applications wherever you want predictive text. You'll notice this when you type in something in any kind of search, or nowadays when you're typing an email, your email will start guessing the next word and trying to help you out. That's based on a language model like an ngram. I've switched to the second notebook for Chapter 8. This notebook will give a little bit more detail behind the scenes in what happens with NLTK's ngrams function, and this will lead us to a discussion of Python iterators and generators. Here in this first code block, I'm asking for unigrams, and then I'm iterating over them. This unigrams variable here is actually pointing to a Python generator. And it's this generator that we can iterate over. That's a long-winded way to say that a generator is also an iterator. Let's look at the bigrams. Here, bigrams is a generator object as well that we can iterate over. The thing about generators is that once you use them, they're consumed and you can't access them again. It's kind of like once you've eaten your pizza's gone. So you've got to buy another pizza. So here, if we want to process those bigrams, we'll have to create another instance. So switching back to the first notebook, that explains why we surrounded the ngrams function call with a list. This will take all of those generated items and push them into a list. Okay, back here. Let's dig a little deeper into iterators and generators. You're very familiar with iterators, even though maybe you didn't call them that. So built-in Python data structures such as lists are iterable. There's a built-in iterator function that goes with them. And that's why you can do things like this. And again, just to reiterate, generators are also iterators, but iterators generally are not generators. We can write our own generators. Here I'm going to show two ways to write the Fibonacci function. One is just our regular way, starting off with an empty list, and we'll keep appending new numbers to our Fibonacci sequence and then return that list. That's the normal way we've been writing programs. If we want to write a generator, we'll do it like this. Instead of accumulating a list and returning it all at once, we will yield the new numbers one at a time. So a generator function doesn't have a return, it has a yield, and each time that it's called, it will result in one item being sent back, and it will basically suspend operation at this point, and next time it's called, it will pick up where it left off. So if we call this function that we just created, what we see is it's telling us that it is a generator object, and we can iterate over that generator object that we create right here. This code looks very strange, and so why would you want to do this instead of doing things a normal way? The reason is memory. Let's say you're processing a huge number of Fibonacci numbers here. This function right here is required to hold all of those in memory, and that can really tank your performance, not to mention use up all your memory. So for processing large data, this would be better because it doesn't hold everything in memory at one time. That's just a little background on iterators and generators. You can just take advantage of the fact that NLTK has written the generator for you, but it's kind of nice to know what it's really doing behind the scenes. So another thing I want to talk about is pickling. So pre-processing a large amount of data is going to be very time consuming. So it's a good idea to take all of that pre-processing and put it in another program, then save its results to disk and then read it back in later. That means that the rest of your programs that want to use that pre-processed data don't have to go through all that pre-processing again. Python gives you a way to do that with pickling. What's a pickle? Basically, it's a way to serialize data, and then if you want to read it back in, that's deserializing it. Here's a minimally working example. I have a dictionary. I'm going to open a file name to write this out. I happen to call it .pickle. That's not necessary. I do need to write binary, and then you do a pickle dump to write it back out there. So the first argument here is the thing that I want to write out, and the second is that handle here for my pickle. Then if I want to read it back in, and typically we'd be doing this in another program, we're going to read it in as binary. And here's my new dict, and I printed it out to show that my new dictionary is the same as my old dictionary. In the last part of the notebook, I have another example of using ngrams. I'll go over this quickly. Here I'm importing some file IDs from NLTK Corpus Project Gutenberg files. I'm going to read in the text of Jane Austen's book, Emma. Here I'm just doing a little pre-processing, getting rid of new lines, then tokenizing and printing out a few tokens. Next I'll create some unigrams and print out a few. Here's a few counts. Agitation is 16. Interesting. And do a similar thing for bigrams. A lot of wind in this novel. This looks a little suspicious. It could be that some kind of footnote ended up being part of the text. We'd have to dig into that deeper. Generating ngrams over a large corpus can be slow using NLT's function, so it might be better to build those dictionaries in a program, pickle them, and then you can unpickle them, reading them back in a different program. And then here's an example of finding the most common bigrams. None of this is very surprising, given what we've learned about language. I have an additional section in the chapter about evaluating language models with a metric called perplexity, which is derived from information theory. Be sure to read that. In the spirit of bigrams, I'll leave you with this quote by C.S. Lewis. "Two heads are better than one, not because either is infallible, but because they are unlikely to go wrong in the same direction."